Morning. So today is the exciting day because we're actually starting doing general relativity. So in order to get here, we have to review some special relativity. Then I gave you some motivation for how general relativity actually was developed, and how, I showed you what Einstein was thinking when he was developing general relativity. And as I told you, it took him basically 10 years. So after 1905, he started working on general relativity after publishing special relativity, and then it took him until 1915, where he finally arrived at the Einstein equations. And of course, one of the reasons why this was so painful is that, of course, he has this incredible physical insight, but he didn't have the math tools. He didn't know differential geometry. And so he realized pretty soon that he actually will need differential geometry to describe the field equations. But simply he didn't know differential geometry, and no physicist actually knew differential geometry. It was just this weird thing mathematicians would do, and even today it's very painful to communicate between physicists and mathematicians, right? So they use different language and like very abstract things. Mathematicians actually think that physics is just a trivial application of mathematics. On the other hand, actually physicists think these mathematicians, they do very weird things. They are trying to prove something which is obvious, and so on. So there's this miscommunication. And it took really Einstein a couple of years and really painful collaboration with Marcel Grossman before we actually land enough differential geometry to formulate his equations. But still, even after he learned this differential geometry, it was still driven by intuition, how to arrive at these equations. And so really, his way, and let's call it Einstein way, or let's following Einstein knows, is precisely what I was telling you yesterday. So he was looking for a tensor, whose divergence, covariant divergence, is 0, because he knew that divergence of T mu nu is 0. And so in the end, he arrived at this answer, firstly without lambda, and then introducing lambda because you can. But it was like really Einstein's way, like really, really physical way how to do it. And as I said just now, it didn't happen in Prague, unfortunately. Einstein left Prague, and then after he left Prague, it took him only a couple of months actually to arrive at the equations of motion. But he was not the first one, and that was the punishment. So actually, Hilbert, the mathematician, was the first one, and he scooped Einstein for a couple of months. And so in some sense, Hilbert's way, the mathematics way, is much more effective. So what I would like to do actually now is that we understand, what the problem is. We understand how Einstein arrived at the solution, and it's a very, very physical way. But now let us look at this much more effective Hilbert's way, how he actually, derived these equations, starting from variational principles. So that's actually now what I'm going to do is that I'm going to arrive at the same equations, but now in the way Hilbert did, and it was much more effective because he had a seminar, and in a couple of weeks he had the answer. All right, so part A. Let's start discussing particle in curved space, and this is trivial, but let's do it anyway. So we know that in special relativity, the motion of the particle is such that it maximizes the proper time, and it leads to the straight lines. So the geodesics in Minkowski space are just straight lines. So now let us just guess that the same thing must happen in curved space as well. So we guess that again, motion of a free particle maximizes proper time. Okay, and so if this is to be true, then our action for the particle must look similar to, well, it's actually precisely the same action as in flat space. However, now we know that our proper time is given in terms of the curve metric, instead of the flat metric. So this is just minus m. Now I use an arbitrary parameter lambda, and then just write d tau. But now now my space-time is curved, so it's minus g mu nu. Of course, that depends on x, on the position of the particle, and then dx mu over d lambda, dx nu over d lambda, and then d lambda is already there. Okay, so this is our action, which we sort of guessed, but you know, what else it would be than the proper time. Okay, so what it means is that, let me denote this derivative with respect to lambda as a dot. So d over d lambda is a dot. And that means that our Lagrangian, which depends on x and x dot, is just minus m, and then the square root g mu nu of x, x dot mu, x dot nu. And then we write down the corresponding Euler-Lagrange equations. So we just write d over d lambda, dl over d x dot alpha minus dl over dx alpha equals to 0. So the calculation now actually proceeds similar way. The only difference is that before we had the flat metric here, which didn't depend on x. It was just a flat metric. And so if you differentiate it, you would just get 0. But now our g mu nu, the curve metric, in general depends on the position of the particle. All right, so now you can calculate dl over dx alpha. Okay, and so the only dependence is hiding in that metric. So it's equal to m g mu nu. Now I differentiate this with respect to alpha, x dot mu, x dot nu, x dot mu, x dot nu, and then I differentiate the square root. So I'm getting 2 times square root in the bottom. All right, so that's what dl over dx alpha is. Now I need to calculate dl over dx dot alpha. So now the metric is a spectator. It doesn't depend on x dot, but I have 2 velocities, so I have 2 terms, which are exactly the same terms. And it simply gives you m g alpha mu x dot mu. And it's 2 times, so there's no this factor of 2 in the square root. Okay, so this is what you get from here. And then finally, I have to differentiate d over d lambda of this thing, dl over dx dot alpha. Okay, so I have 3 terms which depend on lambda. Is this annoying term is the square root, and is the term is g, and is the term is x dot. Okay, so differentiating first the square root, I have that this is d over d lambda, 1 over square root, and then the rest I just write g mu alpha x dot alpha. I differentiated the square root, and then I differentiate the metric g, so it's plus m over the square root, and then g alpha mu over nu x dot nu x dot mu. So the time derivative of my metric is just derivative of the metric with respect to the coordinate and time coordinate dot x dot mu. And then finally, I can continue this thing here. I have to differentiate this guy. And so it gives me g mu alpha x double dot mu. Okay, so that's the 3 terms I get differentiating these things. Very good. So now I just combine everything together. So I have this minus that. Okay, and that equals to 0. So what you can do is that, of course, there's this annoying square root everywhere. So you can multiply everything by that square root. You can also notice that the m appears in every term, so it cancels, of course, and cannot do anything. So m is gone, and the square root I just multiply by the square root. And then you have this strange term, which is like the square root and d over d lambda of this thing here. And that's really, really ugly, so you call it something else. And then it becomes less ugly. So you introduce a function f, which you define to be minus square root d over d lambda of 1 over square root. Okay, so that's just how I simplify my life. It's just so ugly that I call it f, and it's so easy. Okay, so then I have the terms. I have g mu alpha x double dot mu, which is this term here. And then I have this term here. But notice that this term here is x nu and x mu. It's symmetric in nu and mu. So I can equally symmetrize mu and nu here. So I can actually write it as a sum of two terms. So I can write it as plus 1/2 g alpha mu nu x dot nu x dot mu plus 1/2, and now I switch them, g alpha nu mu x dot nu x dot mu. Okay, so that's just writing this term here, but using the fact that it must be symmetric in nu and mu. And then finally I have that term, which is with a minus sign. So it's minus 1/2 g mu nu alpha x dot mu x dot nu. So that's this term here. And then I have also the term which is the derivative. And let me put it on the other side. So this is equal to f g mu alpha x dot mu. Okay, that's just grouping all the terms together. And now you see the beauty. Of course, okay, this is what we want. It has two derivatives, so this is the nice term. But if you look at these three terms together, they are simply 1/2 x dot nu x dot mu times, and now you have g alpha mu nu plus g alpha nu mu minus g mu nu alpha, which I hope everybody recognizes the Christoffel symbol here. So these three terms simply gives me gamma alpha mu nu x dot nu x dot mu. Okay. So for those who came late, we are now abandoning the Einstein's intuitive way of deriving Einstein's equations, and we are switching to variational principles, so the Hilbert's way. So anyway, so we have g mu alpha x double dot mu plus gamma alpha mu nu x dot nu x dot mu, and then this is equal to f g mu alpha x dot mu. So this is what we derived. Obviously, we can now raise the index. So I can multiply everything by, let's say, g alpha beta is the index upstairs, and then you find that x double dot beta plus gamma beta mu nu x dot mu x dot nu equals to f x dot beta. Okay, so this is the equation which follows from varying this action using the lambda parameter, any parameter lambda. Okay, and if you write it in covariant way, of course, this is nothing else than the geodesic equation. However, now with this non-trivial right-hand side. So remember, I told you that we can write down the geodesic equation as something like this, where you would have a non-trivial right-hand side, but it's still a geodesic equation, right? So this is still a geodesic equation, and so this f, which we define over there, of course, is in general there. of course, you can get rid of it by saying, well, let's choose a better parameter than lambda. Let's choose an affine parameter. So affine parameter. So for a massive particle, you can, so for example, the proper time. So if you choose now lambda equals to tau, then of course the square root just becomes 1 from the normalization of the forward velocity. And so if you differentiate 1, you get 0. And so then f is equal to 0, and then we have the equation as we know it. So then we have u alpha nabla alpha u beta equals to 0, where u alpha is d x alpha over d tau. Okay, so you can always choose an affine parameter for which this function f vanishes. But you see that's only just reparametrizing by curve. So this equation is already a geodesic equation. It describes the geodesic, but simply I'm using stupid parameter. And so it's true that even in curve space, so this is of course what we expected from the geometry, but it's true that in curve space still the motion of free particles is such that it maximizes the proper time. So however, notice how we could actually have derived this action is that all we have done is that we just replace the flat metric with the curve metric in the action. Otherwise, it's just the very well-known formula from Minkowski space. And so this is something which we'll call minimal coupling principle. I will talk about it in a minute. Are there any questions? So now we understand particles in curve space from the action principle. Yes?
I'm a little bit lost with the symmetrization of G mu nu.
So all I was saying is that you know that this object is symmetric in nu mu. So now this multiplies this other object which also has mu nu. So I'm summing over mu nu. So if this thing had some antisymmetric part, that would drop out, right? So if I have antisymmetric part in mu nu, symmetric times antisymmetric will give you 0. So that's why what you can actually do, and you don't change the result, is that you symmetrize over here. And it's the same thing. But of course, symmetrization means that I can take G alpha mu nu plus G alpha nu mu divided by 1/2. Well, multiplied by 1/2.
Also, there's another term which is plus, which is a minus, but it's 0. I see. So there's also another antisymmetric.
Yeah. Okay. Yeah. If you want, you can write it. You can write, symmetric. Well, you can write any tensor T alpha beta as the symmetric part plus the antisymmetric part. That's what you are saying. So now the statement is, if I write down this antisymmetric part, because this guy is symmetric times antisymmetric is 0. So this thing will not contribute to that. Other questions? All right. So,
Question.
yes?
Is there any restriction on the function that multiplies x dot on the right-hand side? Does it have to be a scalar or in order for the geodesic?
Well, okay. So this thing is certainly a tensor. It can be written as nabla uu. So the left-hand side is a tensor. This is a tensor, right? This is a vector. So this must be a scalar function. So f is a scalar function. That's certainly true. But otherwise, it's simply some function. But you can always find a reparametrization where this function vanishes. By the way, I told you that you can choose lambda equal to tau, and then it gives you whatever you want. Actually, there is not so much freedom in affine parametrization. And actually, if you find one affine parameter, one tau, for which f vanishes, the other ones will be simply given by a linear transformation of that one. Okay, so it's only those. So now if I have one affine parameter tau, then I can go simply to another one by doing this. where A and B are constant, and that's it. So actually, there's not so much freedom in affine parameterization. All right. So now, geodesic deviation equation so the question is how to describe the strength of gravity. Okay, and so we already know from studying the geometry that somehow the strength of gravity must be captured by the Riemann tensor, right? But what does it mean? What does it mean to have a strength of gravity? Well, I can always go to a freely falling system, and so I can get rid of gravity. And so the gravity which I can get rid of is not really a true gravity and doesn't have any strength. So the strength of gravity, really, what I mean by that is the tidal forces. So the effects which actually appear when I have finite size systems. Okay, so the question is how to quantify strength of gravity, and the answer is by tidal forces. So answer is by tidal forces. So really, what are the differential forces acting on my finite body? So an example, we have that picture of a huge elevator. So this is our huge elevator, and this is our airs. So then you know that the force here will be huge, and the force here will be huge. But if I'm further away, well, then there will be another force here. But if I'm further away, the force will be much smaller because I am simply, it decays like 1 over r squared. So this is how the particles on geodesics would, in rest, would actually move here. Okay, so this is what you see. But now you can sort of get rid of gravity by going to freely falling frame, so inertial frame, local inertial frame. And so what it means is that I take, for example, the middle of my elevator, and I just let the elevator fall with the balancing this force here. I just make the force here 0 by going to the corresponding inertial frame. Okay, so then if that is true, then this is my errors. Now this guy is really falling so that the center actually is exactly balanced, so there is no force in the middle. But of course, if I draw the forces on this line, it'll be like towards the center. So then you will have force like this here. And then, of course, these forces here are much bigger because you are closer to the airs. So then you will have forces like this. But if you are further away and you subtract this force here, you will actually have forces like this. So the statement is these differential forces are really what describes the strength of gravity. This I cannot get rid of by going to the freely falling frame. So this is the strength of gravity, the true strength of gravity. Okay, and I cannot get rid of these things. And of course, these are the tidal forces. Which you know from the interaction of airs and moon through tides of the sea. But this I cannot get rid of by going to the freely falling frame. All right. Well, what it also means is actually that gravity is pretty sneaky in the sense that, yes?
Sorry, I don't really understand the direction of the arrows in the second picture. Could you?
Okay, so this one, for example?
Any of them?
Okay, so what you are doing is that basically you are making this force to be 0. Okay, so that has some magnitude, and it's certainly bigger than these forces here because you are further away. So what you are doing is basically you are subtracting this thing here by taking an opposite vector, and so this is my result, and that's what I'm plotting.
Right.
Okay, but what it also means that if you are a muscle guy, right? So you are really, really big guy, and you have big muscles here, a big belly, and then whatever. All right. Okay, so this is without the gravity. But now look what actually gravity does to you. So if there is Earth here, then there's a force acting on your head and on your body, going this way. It's trying to actually, and then there's a force going that way, right? And so it tries to actually squeeze you. It tries to pull you and make you shorter. Sorry, make you longer, but make you slimmer. So in the end, you have a guy like this, and no muscles at all, and much longer, of course. But this is what gravity does to you. So, on the surface of the Earth, it's very difficult to be a muscle guy. That's the proof. So this is what tidal forces do to you. It's like they try to make you longer, and they try to squeeze you in that direction. All right, so how to quantify these tidal forces? As we shall see, it's by geodesic equation, but we can just think about an example. So example is that, let's say I have a supermassive black hole or whatever, something really, really heavy. So there is this huge black hole somewhere here, and then I have a star, and the star. So there's a star, and the star actually moves around this supermassive black hole. So of course, because the star has a finite size, there will be these tidal forces acting on the star, right? And so there will be bigger force here and a smaller force here, and there will be this effect here and that effect here and whatever. So you should be thinking about. So the star gets deformed. So star gets deformed, similar to our guy, right? So now you want to describe how the star gets deformed, and let's use the simplest possible model for this. So you can just say that the star is actually just a bunch of particles put together, which all of them are moving on geodesics around the supermassive black hole, right? So this particle is simply going on its own geodesic. That particle is going on its own geodesic, and so on. So the model is that the star is just a swarm of particles. Moving on a geodesic. Each of them moving on its own geodesic. On geodesics. And so you start with some initial star, and you just let it evolve around this supermassive black hole, and then you look later, what the shape of the star looks like. In other words, if you have one particle following this geodesic, then because the other particle is somewhere else, and because of the tidal forces, the other geodesic, even if you start with the same direction, will actually maybe go apart from the first one. So actually, the geodesics start actually deviating from each other, and so that's the effect we want to describe. So geodesics start deviating because of the tidal forces. Okay, so that's the physical picture which we have in mind. So now there is very many ways how you can derive the geodesic deviation equation, how you can actually derive how much these geodesics deviate. Really fancy ways. And if you use fancy mathematics, the derivation takes one line. I will not use fancy mathematics. I will just do the pedestrian way, and so that it's actually quite painful calculation. So I will skip the steps. So what we are really trying to do is that this is our manifold, and on that manifold we have some central geodesic. Let's say the center of the star. Okay, and then so that will be this point, and so that point moves on some geodesic here, and then I have some. So this is described by trajectory x mu of tau. I will be using the affine parametrization for the geodesic, and then you have some nearby geodesic. So this is a nearby geodesic. And that will be described. So I can always go from my geodesic x mu of tau by adding some vector delta x mu of tau. And that's how I get my new geodesic. So my new geodesic is simply described by x mu plus delta x mu of tau. And then you are interested in how this vector delta x mu actually changes, right? So if it remains, all the time the same, the geodesic remain, let's say, parallel or whatever, they don't. Now, one effect which is very important is that maybe you can shoot the first geodesic this way, and then the other geodesic that way. So of course, then they are going apart, but they are going apart at a constant velocity. So the velocity of how they are going apart in the velocity terms is not important. What is important is how they are accelerating away from each other. So it's not the velocity which is important, but it's the acceleration. So that I actually don't describe the effect that one geodesic this way, shoot that one geodesic that way. Of course, they deviate, but they would deviate in flat space as well. That's not the effect of gravity. I'm interested in the acceleration. All right. So let's calculate this. And of course, I treat delta x mu as small, so I will linearize everything in delta x mu. So we have two geodesics. So the central geodesic simply satisfies d square x mu d tau square plus gamma mu alpha beta dx alpha tau dx beta d tau equals to 0. That's my central geodesic. And I have already two zeros here. Well, it's still true, but it's better to have only one zero. And then the other geodesic, well, still a geodesic. So it satisfies d square of x mu plus delta x mu over d tau square plus gamma mu alpha beta. So now remember the Christoffel symbols, they depend on x, right? So they are position dependent. So now I have to evaluate these Christoffel symbols at that position x plus delta x. And then I have d x alpha plus delta x alpha over d tau and d x beta plus delta x beta over d tau, and that's equal to 0. So that's the nearby geodesic.
Question?
Yep.
Can you use the same proper time for both the geodesics?
I synchronize my time, then I say, well, whatever. The answer is yes, you can. So the statement is whatever the time is here, and I have this deviation vector delta x mu. I call the corresponding point x mu plus delta x mu. I call the corresponding parameter of this geodesic tau again. Okay, so yes, you can in this way. So by construction, I am choosing this description here. All right, so we have these two equations, and we want some equations for this deviation vector delta x mu, and so we better subtract these equations, right? So subtracting, of course, I better take plus this one and minus that one. You find a simple equation. So this term cancels that term, and all I have is d square on delta x mu d tau square. That's from the first term. And then I'll be only doing, I'm doing linearization. So I'm throwing away all the terms which are higher order in delta x mu. Okay, so now if I look at this term here, I can do a Taylor expansion on my Christoffel symbols. So there will be a derivative of the Christoffel symbol times delta x. And then, because I already have delta x, I just take this term, and that's something which will be new. So I have a term plus delta x rho d rho of gamma mu alpha beta now in x, and then just x dot alpha, x dot beta. Okay, that's the term I have. Of course, the zero order term without any delta x will cancel that term, right? So now I have only the linear in. Okay, so that's the term by expanding gamma, but I also have the term when I have this thing here, and the terms are the same. So again, it's symmetric in alpha and beta. So I have plus 2 times g mu alpha beta in x again, and then x dot alpha, and then I have d over d tau delta x beta equals 0. Okay, so just by subtracting these two equations and keeping only up to the linear in delta x terms is the equation. So this is already a geodesic deviation equation. It tells me how this delta x mu is evolving with my proper time as I move along the geodesic, right? So you could say this is it. But of course, the problem is that you have these gamma terms, you have the derivatives, and then you have normal derivative here. So this is not a tensor equation. So this is a good equation to solve in given coordinate system, but it's not a tensor equation. So to make this a tensor equation, you want to write this term here covariantly. Okay, so that means that instead of small d, I'll be using capital D. And so it's pretty simple. So now what you do is that you just look at the acceleration, so covariant acceleration, and that you define, simply you replace small d by capital D. You replace partial derivatives with covariant derivatives, so it will be d squared delta x mu over d tau square. Of course, you have to apply the covariant derivative twice, and so it's d u mu over d tau. That's application once plus gamma mu. I'm missing some indices. Alpha beta u alpha x dot beta, where this u alpha is d delta x alpha over d tau. Okay, so I just did explicitly one derivative, but I still have another derivative here hiding. Okay, so it's obvious that if you plug this u here, so u appears here and u appears here, and I have to expand that covariant derivative as well. Okay, so if I do it, then schematically, this is equal to, So d square delta x over d tau square. So if I plug it there, so just do it. It's two-line calculation, but it's just too messy to write it down. It's just too many indices. So if I plug it that u alpha here, I will have term which has two partial derivatives. So that will be d square delta x over d tau square. So there will be such a term. And then there will be the following terms: 2 gamma x dot d over d tau delta x. That's another term which will appear. And then you have a derivative of gamma term here. And then x dot delta x. And I did a huge mistake because you will not be able to see it, but maybe, yeah. And then you have terms gamma gamma, and then x dot delta x. So this is schematically what you get if you do, if you write it down explicitly. By the way, this gamma gamma term, this minus, comes from the fact that at some point I have to differentiate x mu twice. So I'll be using my geodesic equation again. And so if you have x mu double dot, it's simply minus gamma x dot, and that's where this minus comes from. So anyway, so these are the terms. And this is what it is. So now let's look at the equation which we derived. And so we arrived the equation which was, the deviation equation, but not in covariant form. But it has d squared delta x mu, so it has this term here. And it has the term 2 gamma x dot delta x dot, which is precisely this term here. Okay, and that's why I put the 2 there, so that's very convincing. And you see that these two terms together, they just give you a term which looks like delta x with a minus sign, delta x, and then d of gamma, and x dot. So they give you the middle term here, right? So if I use that equation, then these two terms together, they just give you a term minus delta x d gamma x dot. Very good. But now you see that this term, so let's just these two terms together. Okay? And there is an important minus sign. So see, we forget about all indices, we forget about everything, but the minus sign is important. Okay, so now this term plus that term, well, they are of the same type. They have x dot, and delta x in them. So I have x dot, delta x in them, and then I have d gamma minus d gamma. Okay, so in other words, if you combine this everything together, what you find is that this is equal to, and this is not good, I'll write it here. So what you are getting is that d square of delta x over d tau square equals 2. And now you have the term simply d gamma minus d gamma plus gamma gamma minus gamma gamma x dot delta x. Okay, that's what we are getting out of that, so schematically. So now anybody recognizes whatever is inside the bracket. It's the Riemann tensor. Excellent. So this is the Riemann tensor. And so you can really fill all the steps, fill all the indices if you want, but this is the right result. So now let me write it with indices. So the result, if you keep track of all the indices, this is what you get. So d square, the acceleration of how my geodesics actually deviate from one from another, is given by the Riemann tensor r mu alpha beta nu delta x nu x dot alpha x dot beta. And this is called a geodesic deviation equation. geodesic deviation equation. And you know, this really tells you that the Riemann tensor, which of course is really, very crucial part on the right-hand side, describes these tidal forces of gravity. That describes the true gravity. That describes the effects I cannot get rid of by going to the inertial frame. Okay? So this is very, very powerful equation. And I would say this is really the physical meaning of the Riemann tensor. Okay, before we had the mass meanings of the tensor. If I parallel transport a vector, I may not get to the same vector as I started with, but I may rotate around it. That's the geometrical meaning of the Riemann tensor. But this thing is really, really physical, how the gravity works. Okay? So Riemann tensor describes the tidal effects.
In that equation, where is the Riemann tensor being evaluated?
That's a very good question. Thank you so much. So remember, we were expanding everything to the linear order in delta x mu, but so that means that we are plugging everywhere x, right? In the end, it's not x plus delta x, but it's plugging x. So we are, if the picture is still there, so we are evaluating everything back on my central geodesic. So all the quantities here. So the Riemann tensor is function of x, but x is a function of tau. Okay. Similarly, x dot is a function of tau and x dot. So everything here is evaluated on central geodesic. So actually, this is a pretty nasty equation. The equation is linear, right? We are trying to solve for our deviation vector delta x mu, right? And so it appears here and it appears here. So the equation is simple and linear. However, it's a differential equation, second order differential equation, but everything here depends on time. Everything here depends on where on the geodesic I am, on my central geodesic I am. So this Riemann tensor has to be evaluated on the geodesic, and so these things here. So in order to solve this, first, you need to know what the central geodesic look like. So you need to know the solution x mu of tau. Okay, and then once you have x mu of tau, you also know what the metric g mu nu of tau is, because g mu nu x of tau. So what is the value of the metric on the geodesic? And then you use this metric to calculate the Riemann tensor through this horrible formula here. And so you get something which is, again, a function of tau. And it's pretty nasty to solve. In fact, in the whole history of general relativity, there's only a couple of solutions known to this equation. Okay, but you know, I think it's really, the meaning of this equation is it gives the physical meaning to the Riemann tensor. Okay, so the Riemann tensor, Riemann describes tidal forces. Tidal forces. So by the way, it may happen that in your space-time, okay, first of all, tidal forces. So the Riemann describes tidal forces. So now you may be asking how big the tidal forces are in different objects. And so let's say I imagine something really, really beastly. So I imagine a huge black hole. Okay, I have a huge black hole and I am on the horizon of that black hole. Do you think the tidal forces are big or small? Okay, the answer is they are small. And the reason is that if I have really, really big black hole, well, its horizon or surface looks almost like a plane, right? And if it looks almost like a plane, well, all the forces will be pointing the same direction. So if I go to the freely falling frame, I don't see any gravity. So big black hole, horizon of a big black hole has small tidal forces. In fact, according to GR, nothing really happens as you cross the horizon of the black hole, as we will discuss next week. So we may be, at this very moment, we may be passing through a horizon of a big black hole, and we wouldn't notice anything, right? Because the tidal forces are simply too small. And if you are freely falling, then we don't see any effects of the gravity. Okay, we only later realized actually we passed through the black hole and we cannot go back. Okay, so this is possibility. Was there a question?
How the tidal forces in this direction?
Yeah, so there will be some tidal forces which will be doing precisely to the muscle guy, or whatever I drew here. But because the surface is basically planar, these effects will be really, really small. So yeah. However, if you have small one, of course, the small one looks like this, and the tidal forces will be big. So beware of small black holes. Because the small black holes will precisely squeeze you like that. Okay? Because the tidal forces close to the small are really, really huge. Okay, the last remark I want to make is that sometimes it happens that you cannot solve geodesics in the space-time, but maybe you solve for one. Okay, so really I want to describe, for example, the motion of the star, but this black hole is a complicated one. There are some perturbations and stuff like that, and so maybe I can only solve for the central geodesic. Okay, so then can I actually? So typically, I cannot find all the geodesics in the space-time. Maybe the motion is not integrable or whatever. Okay, but what you can do is that you can still solve for the deformation of the star by using this geodesic deformation equation. So if I know how my central geodesic looks like, for example, the motion in the equatorial plane or something really, really simple, then if I can solve this equation, let's say numerically or whatever, then I can find the nearby geodesics because I know that they are given by delta x mu, which I know. So I can find the nearby geodesics by doing this thing, by solving this equation, and then I know, a couple of geodesics, how they behave in the space-time. And then I can say what's happening with my star. Okay, so even if the motion of geodesic motion is not integrable, and I cannot solve for all the geodesics, I can use this equation to tell you about the deformation of objects and stuff like that.
What defines small? What's the relevant length scale?
The
smallest of the deviation?
Well, everywhere I treated delta x mu as I expanded to the linear order in delta x mu, right? So as long as delta x mu square is much smaller than delta x mu, this is fine.
David, would the effects of a big black hole on a big thing would be the same of a small thing near a small black hole? Because
you like to compensate small with small.
Yeah, because if you just zoom in, you would see the same.
Of course, so if you have a big black hole around a big black hole, of course, because the object itself is big, the tidal forces will be significant because the field will be different here on one side of the star as on the other side. Yeah, so there'll be significant deformation. Yes.
So does that answer the previous question? What's the length scale? The length scale.
What's the length scale? Okay, you figured it out yourself. I'm just saying whatever I derive was like a linearization. So this is true as long as I can neglect delta x mu squared, right? Whatever that means. Okay. All right. So now we understand the geometrical meaning of the Riemann tensor. And we understand everything about geodesics. By the way, very recently I wrote a paper that which is a trivial result, but I wrote it in a language that nobody understands, and so the paper was published. So it's about basically integrals of motion for this horrible geodesic deviation equation. So, and you can of course show that it's a trivial thing, is that if you have the motion of geodesics integrable, so you have lots of integrals of motion for your geodesics, and you can integrate for your geodesics, then surprisingly, all these integrals of motion descend to the integrals of motion of this equation. It's a trivial result, right? If I can solve for all geodesics, I should be able to solve for the nearby geodesics, right? This is a trivial thing. But anyway, actually, I haven't seen it anywhere in the literature. And actually, the proof is quite interesting. So really, the full integrals of motion of geodesics descend by linearization to integrals of motion of this geodesic deviation equation. But it's written in a language nobody will understand, so it's good. All right. Part B, matter in curved space. By the way, by space I mean space-time, of course, right? So we discussed the geodesics, so just the point particles in curved space. But now, if you want to discuss any matter in curved space, what typically people do is that they invoke a principle which is called minimal coupling principle. Which is equally vague as quantization of fields, as quantization in quantum mechanics and whatever. So again, in quantum mechanics, you are trying to arrive at quantum laws starting from the classical physics, and that cannot be done, but maybe there's some guiding principle which helps you to find the right answer. So similarly here, the minimal coupling principle is telling you, well, if I know the laws in special relativity, then I get the laws in the presence of gravity in general relativity by simply replacing the flat metric. Whenever I see a flat metric, I put a curved metric, and whenever I see a partial derivative, I replace it with a covariant derivative, and that's basically it. Okay, so I just make the laws in special relativity to be like really tensorial laws, to be covariant laws in terms of tensors, and then this is the guiding principle. Okay, so now, as I said, this is very, very vague, and it cannot be done, right? The right way again is I know how my laws look like in the presence of gravity, and then I can take the flat space limit, but not the other way around. And so it's nowhere actually clear that maybe in the same way I could as well add some curvature terms. So, for example, if I'm studying the scalar field theory and I add a term which is scalar times phi square into my Lagrangian, of course this term vanishes in the flat space limit, and so the law will reduce to my flat space case as well, right? But of course, again, you are trying to keep it minimal. So unless there is really something telling you should include this term, you don't typically include that term, right? Unless you have to. But as I say, this is not. It's very, very vague, and it's not, how you really derive these laws, because these laws cannot be derived. It's just, how you guess the result, and then the final word, of course, is up to the experiment, right? So I guess some form of the equations, and then I derive the consequences, and then I compare with the experiment. Okay. Questions to this? So then, once we do this, we can invoke the action principle. And so we want to describe what is the corresponding action for matter in curved space. So this is action for the matter. And so in flat space, it would simply be, in d dimensions, it would be ddx. And then the Lagrangian density for my field, so phi, and then there will be partial derivative of phi, which I change by this minimal coupling principle to a covariant derivative of phi. And in principle, this can also depend on the flat metric, which I replace with my curved metric G here. So this is a scalar. But we learned 2 lectures ago that if you just integrate over the space-time dimensions, this is actually not a scalar. And you need to add the square root of g, where this is the determinant of the metric. So this is the invariant volume element. And that's it. So this is how you write down the action for the matter in curved space. So just replacing partial derivatives of the field with covariant derivatives, replacing the metric with the curve metric, and putting the invariant volume element here. All right, so now we have this action here. And so we derive the corresponding Euler-Lagrange equations. So we vary this action, delta Sm. So now in order to derive the equations of motion for the matter, you just differentiate. Well, you vary this action with respect to the field, right? So this is delta field of the matter action, and it's equal to. So now you can write it symbolically as d dx delta Sm over delta phi. Of course, what it practically means is that this is d4 d dx square root of minus g, and then d Lm over d phi delta phi plus d Lm divided by d nabla phi delta nabla mu of phi. Precisely what we were doing in classical mechanics. All right, so we just varied the action with respect to both phi and nabla phi. So now we want to, as always in mechanics, we want to swap the order of delta and nabla mu, but we can still do it. So again, this is true, nabla mu delta phi, because the variation of the field has nothing to do with the space-time. Okay, so this is still true. And then we would like to move this derivative here onto that term by integrating by parts, as we are used to. Okay, so next, we want to integrate by parts. And the statement is we can still do it, and there is a corresponding mathematical theorem that you can still do it. It's, again, the Stokes theorem. So again, there is a Stokes theorem, which tells me that if I want to integrate nabla mu of some vector over the space d dx, then this I can turn to a surface integral. So d sigma and mu b mu. Am I missing something here? Probably the square root of g. Maybe. Okay, so I'm just turning a volume integral into the surface integral. But what it means in practice is that if I have the following expression, a mu nabla mu acting on b, square root of g d dx, then I can write it, I can shift the derivative from b to a. So this is an integral nabla mu a mu on b square root of g d dx plus the surface term. Okay, this looks fancy, but what it means is that I can integrate by parts. Okay, up to a boundary term, which is this one here. But if I don't care about the boundary term, I can integrate by parts into the space.
Isn't there a minus sign?
minus sign. Yes. Thank you. Of course, if I integrate by parts, I get a minus sign. Thank you so much. All right, so we can do it. And if you integrate by parts, then our delta phi of Sm is simply, well, I'm just moving the derivative nabla mu from delta phi on the derivative on d over dl m over d nabla phi. And so I have an equation is d dx square root of minus g, and the first term remains the same, dlm over d phi, and then it's minus nabla mu dlm over d nabla mu phi delta phi plus a surface term. Okay, and so then my Euler-Lagrange equations are, as you would expect, this is equal to 0, and it's precisely the same thing as we had for the field theory in flat space, except again you replace the partial derivatives with the covariant derivative. Okay, so that's my Euler-Lagrange equations. dlm d phi minus nabla mu dlm over d nabla mu phi equals to 0 are the equations of motion for the matter in the curved space. Questions, comments? Yes?
I know in electromagnetism you can have dynamical gauge fields, so by analogy you can also have dynamical metric.
Oh, very good. Exactly. Yes. You, very good. So, give me 2 minutes. I'll get to it. Okay. So here, in the above, I just varied my matter Lagrangian with respect to my field, with respect to phi. However, as you point out correctly, I can also vary it with respect to the metric, right? So let's see, what do I get? So the variation with respect to the phi has to give me the equations of motion for my phi. But variation with respect to the metric can give me something strange, right? So here I'm still not including the gravitational part of the action. I'm just talking about the fields in the curved spacetime. So in some sense, I shouldn't be varying the metric g, or if I am, does it have any physical meaning? Okay, so now let's see that it has some, and that's the meaning of energy momentum tensor. Energy momentum tensor. All right, so now you take the same matter Lagrangian, the same matter action, but now you vary that with respect to the metric. Okay, well, what is this equal to? Well, it's an integral over something where I vary the metric, right? So in the end, I have to have delta g mu nu. Okay, so I'm varying the metric, and so that's why I have to have delta g mu. Okay, so now this is the integral over the space-time, so d dx. Okay, in order this integral to be well defined, I have to have square root of g. So I have my invariant volume element. Okay, and so then this integral has to be a scalar function, right? So I have now two indices delta g mu nu. So I have to somehow kill these two indices by contracting with another tensor, which is indices mu and nu. Okay, let's call this tensor t mu nu, and for reasons which I will not explain, there is also a factor minus 1/2. Okay, so this is what you have to get when you vary your matter action with respect to the metric. And you know, whatever you find here has to have two indices, mu and nu. It has to be some tensor in order this to be a scalar. And this is precisely what we call energy momentum tensor. So now you will learn very soon that actually this is not enough to tell you. There is 101 energy momentum tensors in theoretical physics. We have already seen canonical energy momentum tensor, right? Which was the thing which we derived in flat space by using the fact that my field theory is invariant under space-time translations. And then using the Noether's theorem, we could derive the corresponding canonical energy momentum tensor. So we have seen, well, we didn't calculate it for the scalar field, but we did calculate it for the electromagnetic field. If you calculate it just using the Noether's procedure, you get something, you get some t mu nu, which is conserved. So partial mu t mu nu equals to 0, but it's not symmetric. It wasn't symmetric, and it wasn't gauge invariant, right? So then we could actually cheat, and we could say we can upgrade this by adding some other terms which are automatically conserved, so that the result is actually symmetric and is gauge invariant. So now look at this prescription here. So certainly this tensor which we are finding here, because the metric is symmetric in mu and nu, so this tensor is automatically symmetric in mu and nu, and it's called Rosenfeld's energy momentum tensor. I will not use really the terminology. I will only use the terminology energy momentum tensor because it's the right energy momentum tensor. It's not the canonical one. This is the one which couples to gravity, and this is the one which has nice properties. Okay, so it's this thing here. Okay, there are other energy momentum tensors, and as I said, you will see many more energy momentum tensors. But this is like the one which is important for gravity. All right. So now the statement is, of course, if this is to be important for anything, this tensor better be conserved. So statement theorem is that this thing automatically satisfies nabla mu t mu nu if the matter equations are satisfied, if the field equations, for matter hold. So if you have, maybe I just formulated the other way around, doesn't matter. So if the equations of matter, if the field equations, if the Euler-Lagrange equations for the matter hold, then this thing will be 0. Nabla mu t mu 0. So this is conservation law. Conservation of the energy momentum tensor. Nabla mu t mu equals to 0, provided the field equation hold. Okay. This is really misleading. People call it conservation law, but as we will see, nothing is conserved. Okay. So what this equation is a lot of things, but certainly is not a conservation of anything. But anyway, because it has this analogy with whatever you know from flat space, d mu t mu nu equals to 0, and this gives you some conserved quantities. It gives you some, conserved energy and conserved momentum and whatever. And this is just replacing partial derivative with the covariant derivative. People still call it conservation law, but the truth is that nothing is conserved. Okay, so just a warning, and you will see why and what's going on tomorrow. Okay, so now why is this conserved? Why is this theorem true? And people typically give the following argument. So why is this conserved? And the statement is, it will not be always conserved. It will be only conserved provided that I can write down the action principle like this, where Lm is really a scalar quantity. So if it's a scalar quantity, the whole action for the matter is a scalar quantity. And as a scalar, it's a diffeomorphism invariant. Okay, so if I change coordinates, this thing remains the same. Okay, so consider a diffeomorphism. I didn't say what it is, but it's basically a coordinate transformation, morphism, which I can infinitely write as I'm going from coordinates x mu to coordinates x mu plus epsilon is small and psi mu is some vector field in my space-time. So you can take such a coordinate transformation generated by this vector field psi mu. Okay, and then what happens is that if you change the coordinates, of course, my field may change. So I will have, so this induces some variation in my field, whatever that is, and it induces some variation of the metric. Okay, if I change coordinates, the components of the metric will change by my transformation law. Okay, and so you will derive in your tutorial tomorrow that this delta g mu nu is, if I have such a coordinate transformation, is given by epsilon times 2 times nabla mu psi nu symmetrized. Okay, so this is what you will derive tomorrow. So if I have such a coordinate change, and this is how my metric components change. They just change on by a derivative of this vector field and symmetrized over mu and d. But my action is a scalar. But action is a scalar. And so that means that the action cannot change because the scalar remains the same under whatever the coordinate transformation I do. Okay? So what that means is that 0, again, no space. Running out of space and time. It's too bad. All right, so action is a scalar, so it doesn't change. So under coordinate transformation, so this must be true. The variation of the action is 0. But what is the variation of the action? Well, it's a variation of the action with respect to phi, delta phi, plus the variation of the action with respect to g mu nu and delta g mu nu. All right. Then I'm saying, let's assume that the equations of motion are satisfied. So what does it mean? So I got the equations of motion by varying phi, right, with respect to the field phi. So whatever stands here, this guy's my equations of motion. So this thing has to be 0 because of the equations of motion are satisfied. Okay, so the first term has to be 0 because I'm imposing that I'm on shell, the field equations hold. Okay, but the second term, remember, it's just a, I vary my action, the matter action, with respect to the metric, right? But this is precisely how I define my energy momentum tensor. I varied my action with respect to the metric, and so this must be equal to -1/2 integral d dx square root of minus g mu nu delta g mu nu, right? So this is how I define my energy momentum tensor. It's just a variation of the action of the matter action with respect to the metric, and this is what I define. Well, very good. But now remember that my variation of the metric, the change of the components of the metric, is simply induced by my coordinate transformation. So this is true. Okay, so this thing here is just epsilon, nabla, mu, psi, nu, and then symmetrized. Okay, and there's a 2 factor of 2. Sorry for that. So factor of 2 is very important because it cancels 1/2. And then we have that this is equal to minus an integral d dx square root of minus g. And there's also epsilon here. Minus epsilon d dx square root of g. And then remember, the way we define it, the energy momentum tensor is automatically symmetric in mu and nu. Okay? So again, I can take an anti-symmetrization here, it doesn't do anything. Right? So I can actually get rid of the symmetrization here and it's still the same thing. Okay, so this is T mu nu, nabla mu, psi nu, because T mu nu is automatically symmetric. But now I can integrate by parts. Right? So I can the integration by parts. Simply shifts this derivative from psi into a derivative of T mu nu and brings a plus sign. So this is equal to plus epsilon d dx square root of minus g and then nabla mu T mu nu psi nu.
Boundary doesn't matter.
Plus boundary term. Yeah. Doesn't matter. Okay. Well, very good, but the whole thing is equal to 0. And this must be true for any coordinate transformation, so for any psi. Okay, so the only possibility is that this guy is 0.
When you do the integration by parts, why don't you also get the derivative on square root minus g?
It's simply how the Stokes theorem works in the presence of g. So you can really show, if it's still here, so the way how the integration works is that it doesn't touch the g basically, right? So it's like whatever so you can think about this thing here as really the invariant volume element, and then I can integrate by parts whatever stands in front of it. So that's the mass thing. Okay. So now you see that really, as long as your matter Lagrangian, or as your action for matter is actually the diffeomorphism invariant, is invariant under coordinate transformations, then the corresponding energy momentum tensor defined that way will be conserved. Okay. Isn't this beautiful? So we have automatically conserved energy momentum tensor, which is automatically symmetric. Okay. That's the energy momentum tensor which couples to gravity. So let me just have an example. Scalar field in inner space. Well, okay, all I have to do is to tell you what the corresponding Lagrangian density looks like. And so the statement is, you will see that in flat space, well, you will see a different sign. Because people doing particle physics don't know what they are doing. Nabla mu phi, nabla mu phi, and then minus mu phi. So I have this minus sign here because my metric is minus plus plus plus. But high energy physics people will have plus minus minus minus, and then they wouldn't have the minus sign here. But you know, this is just nabla phi square as you know it from flat space. The only thing is that I replace the flat metric with the curved metric, and this is my potential for the scalar field. Okay, so now if you write down the Euler-Lagrange equations, which are still here, all you have to do is differentiate with respect to phi. Only the potential depends on phi, so that gives me a derivative of the potential. And then I have to take the derivative with respect to the gradient of phi, and it gives me another gradient of phi, and I have to differentiate the gradient of phi, and so I get gradient phi. And so the corresponding Euler-Lagrange equation, Euler-Lagrange, is just nabla mu on phi, so the covariant box operator minus dv over d phi equals to 0. Okay, so this is the corresponding thing. Of course, if the potential is equal to 0, you just get massless Klein-Covalent equation. So if V is m squared phi squared, you will get massive Klein-Covalent equation. But now in curved space. You can also easily check, and I'll give you that to check as a homework, is that if you calculate the corresponding T mu, okay, then you'll find that it equals to nabla mu phi minus plus L G mu. So whatever the L is here, this is the corresponding energy momentum tensor, and it will be conserved. Okay, so to derive this, you need the identities which you discussed in your tutorial on Monday. So they are really far-reaching identities. So if you want to try to derive this, you will need to know how to differentiate the determinant of the metric. Because of course my action is L times square root of minus G. And so you need to differentiate that minus square root of G as well if you vary that with respect to the metric. Right? So, and then you have these beautiful formulas which you derived in your tutorial. So using that delta square root of minus G is minus 1/2 square root of minus G mu delta G mu. And also, if you want, for some stupid reason, not vary the metric with indices upstairs, not with indices downstairs, then the variation is given by a minus sign. G mu alpha, G nu beta, delta G alpha beta. So these are the two identities which you need typically to derive any energy momentum tensor whatsoever for any theory. And so in particular, you definitely need the first one to derive that T mu. So now you will see that this is the T mu, which is the flat space limit, so setting G mu equals eta mu, and the covariant derivative equals the partial derivatives, which you will use in your field theory course. Okay, so that's the corresponding T mu. So this coincides with the canonical energy momentum tensor for the scalar field in flat space. All right. Similarly, you could do the Maxwell theory. So Maxwell, and simply the action would now be an integral dx square root of minus g, and then I have always this stupid factor minus 1 over 16 pi. 16 pi, sorry for that. So it's minus 1 over 16 pi, and then you would have f mu nu, where f mu nu is composed of the potential d mu a mu, and of course the principle tells me I should be writing that, but you can easily check that it doesn't matter which one you write. If you write covariant derivatives, partial derivatives, because the connection will vanish, provided it's a crystal connection. Okay, so now this is the action, and then varying this action with respect to the field A mu, you will get the Maxwell equations in curved space. So you will get nabla mu f mu equals to 0, or as you know from yesterday, you can also write it in this very nice way that the metric only enters to the determinant. Mu equals to 0, that's the same thing. And the other equation is just the star, or what's that equation in terms of the potential. But what is real fun is now to just vary this action with respect to the metric, right? And so the metric enters here to the square root of minus g, but it also enters through rising index of f mu nu. So when I actually write this, I have to write it as f rho sigma, and then G rho mu, G sigma nu. Right? So now I have the dependence of the metric here, and also have inverse metric here and inverse metric here. So now you vary with respect to the metric, it's a one-line calculation, and you find the right energy momentum tensor for the electromagnetic field, which is symmetric and gauge invariant. It's the improved tensor for electromagnetism. So this is really, really nice. Yes.
I'm a little bit confused with the minimal coupling. Minimal coupling means that there's no back reaction in the metric due to the presence of the fields, or?
No, so minimal coupling basically just tells you how to couple things.
Yeah.
And also what it will imply is that the Einstein equations actually will take the form which I was writing down, that
Wait, T mu.
is T mu on the right hand side. But what is actually also automatically assumed there is that if you look at that action principle I wrote there, I'm saying the action of matter depends on the metric. But what I actually didn't tell you is that it cannot depend on the derivative of the metric. If it depends on the derivative of the metric, you will actually get much more ugly Einstein equations. So what is actually automatically assumed is that the metric Lagrangian, the only thing which how the curved space can enter is through the metric itself, but not through the derivative of the metric. If it did depend on the derivative of the metric, you would get much more ugly Einstein equations. And so the fact that G mu nu equals to phi G T mu nu is a nice form where the matter is on the right hand side only, and whatever gravity is on the left hand side is in some sense consequence of the fact that and so that's what's called minimal coupling. Is that whatever the matter is, I can put on the right hand side and then don't care. So let me just write this f mu alpha minus 1/4 G mu nu f rho sigma f rho sigma. So this is the correct energy momentum tensor, and you can easily check that you will get it from that action. Questions, comments? Well, maybe I didn't explain that well. I'll think about it, but it's all it's related to. Yeah. Questions? No. So yeah.
Minimal coupling is part from gauge theory, where we have, for example, electromagnetism, we modify the normal derivative to derivative.
Yeah.
So is it the same?
Yeah, the terminology comes from there as well. Okay, well, see you tomorrow then.